Start the recording. So Sunit will tell us about moduli spaces across geometric transitions and UN equals 1 dualities. Please go ahead.
Yeah, first of all, thanks to the organizers for organizing this seminar series and inviting me to speak here. I'll be talking about a program about n equals 1 dualities which we are pursuing at Virginia Tech. The title of my talk will be Mapping Modular Spaces Across Geometric Transitions and New n equals 1 dualities. So this is based on the work with Lara Anderson, Callum Brody, James Gray, and Quimin Scanlon. I will mostly be covering material presented in this recent paper. However, there'll be like other interesting results, which I'll be talking about at the end, and extensions, which will soon be out in these papers. So let's begin with some motivation. So motivation for pursuing this direction. In general, dualities in string theories are important, and they help us identify redundancies in the string landscape and also achieve computational controls. There might be some couplings, for example, which are easier to calculate on one side of the dual theory and notoriously difficult on the other side, for example. In n equals 2 theories, dualities resulting from flop transitions and mirror symmetry have been well understood. Similar possible dualities in n equals 1 context remain unexplored, but there are interesting recent results and progress, which I'll be reporting on today. Hints of dualities in n equals 1 context come from study of the 02 GLSMs, giving two theories with matching massless spectra. I'll talk about that in a bit. In this work, we primarily use geometric transitions as a tool to understand this duality, studying Calabi-Yau compactifications connected by these singularity transitions. So geometric transitions which involve singular limits. So geometry goes through a single limit. That's what we refer to as conifold transitions here. And there was a conjecture by Reed, often referred to as Reed's fantasy, saying that all such Calabi-Yau geometries in the landscape can be connected in this way. So what are the n equals 1 challenges? The n equals 1 challenges which has halted progress in this direction is presence of this additional gauge bundle. NS5 branes could be there. And then the aspects of 4D EFT, particularly the Killer sector, are not known. So as I mentioned, there are hints of the n equals 1 duality which we get from this study of 02 GLSMs. Particularly what we have through looking at, say, the superpotential in the 02 GLSM is we get in the target space, we get a pair of manifold and bundle, which are distinct sort of compactification and gauge bundle. Nonetheless, they in 4DFT share this singlet count. The massless singlet spectrum matches. And this was first observed in this Dissler-Kachru reference and then recently presented very nicely in this Blumenauer paper. How does one achieve that? If we look at the superpotential, then there are two sets of polynomials in there in the 02 GLSM superpotential. One corresponding to the Calabi-Yau defining equations, and the other are the bundle polynomials, which are like the monad maps, monad sequence being used to define the bundle. And one can relabel them and exchange their roles. And if one does that, we get in the geometric phase, we get distinct target spaces. And however, the non-geometric and hybrid phases are shared. It turns out that such theories are connected by conifold transitions. There's no explanation of this link. An enlightening sort of result, which was studied recently by Anderson, Brody, and Gray in 2022, is where they showed how to take a pair of manifold and bundle through the conifold limit. Particularly the geometric sort of procedure of taking the bundle through is pretty intricate, but I'll try to give you a flavor to just ground us for the further discussions which come in this direction. So what we do is we establish an explicit modular map across these transitions. And this goes much beyond the general sort of manifold and bundle polynomial exchange as we see in GLSM target space duality. And also like the massless spectrum. So we track degrees of freedom in the equivalence classes of these moduli rather than just counting the dimensionality of those cohomology groups. So I begin with just overviewing conifolds in general. So conifolds could be understood via this small cartoon here, where these pointy points are the nodal points or the conifold singularities. And the way to sort of correct them is twofold. One is we could smoothen them out, or we could sort of attach uh, p1s on them. Uh, a simple way to look at it is in simple p1 split examples. If we assume the two defining polynomials of our manifold to have this form, then the nodal limit or the singular limit is given by the determinant of x, u, v, and y vanishing. And we can smooth away from the nodal point by introducing this kind of a perturbation. And this is geometrically equivalent to smoothing through S3 and attaching P1s on the singular points. As I mentioned, this process is intricate in the heterotic context because of the presence of extra gauge bundle. To understand that, we look at the Bianchi identity, the usual one, and then anomaly cancellation condition just gives us a condition on the churn 2 on the tangent bundle and the gauge bundle. So this I call the gravitational sector. This is a gauge sector, and when there are no fibranes present, then this is simple. However, we observe that if there were to be a change on the gravitational side by this class of P1s, then there has to be an equivalent change on the gauge side as well. And it becomes more interesting in presence of fibranes, which are supported by curve C. So we have to add a curve class as well on the gauge side. So I will explain how to take the bundle through just by looking at C2s. But before that, let me just just give an overview of this result, which came out in 2022. It was observed that this gauge bundle breaks up into a spectator piece and an ideal sheaf. The spectator piece remains kind of dormant and spectates through the transition. And the real action happens on this ideal sheaf. So particularly this is again approximate picture. There's much intricate details. I would refer you to go and look at this paper. But what essentially happens is the curves align in the nodal limit. The curves supporting this ideal sheaf, they align in the nodal limit. And there's a jump in dimension, and then they become divisors. And this is where this so-called brane recombination process happens, where the P1 classes we added, they get absorbed into, say, for example, we're going from resolution side to deformation side. This class of P1s get absorbed in the brane supported by the aligning curves. And we get what we get is the ideal sheaf, and the spectator comes through without changing. What we get is the ideal sheaf on the deformation side and the spectator, which when we take it away from the nodal limit gets smoothened to give us the deformation gauge bundle. And this can be seen in this again. The curve on the two manifolds on both sides aligning. It can be seen in this graphic. Here's a flow chart which explains what I just said in terms of C2s. So any change in the gravitational sector has to be compensated by similar change in this P1 classes, for example, on the gauge sector. And then the brane recombination is basically absorption of this into the fibrane supported on this aligning curve. And once that happens, then we have a new set of normal bundle to the curve. And then the ideal sheaf and the spectator recombine after smoothing the singularity to give us the bundle on the other side. So this is a very sort of crude overview of the process or procedure described in that Anderson-Brody-Gray paper. So let me overview the example which we will be sticking throughout this talk. It's a modification of a quintic, particularly written in the historic ambient space way, where we have the usual 5 coordinates, and then I've added a coordinate of weight 1, 3, and a redundant polynomial, vanishing polynomial in the ambient space of degree 1, 3. And the bundle is the usual gauge bundle, the tangent bundle, and I'll deform it. On the resolution side, we have these 1, 2, 1, 4 polynomials, and one way to see them, how we get that is by looking at these F maps, because the GLSM story told us that we can just exchange the manifold and bundle polynomials. So if you look at the F maps here, if you add like this right in like a deformation of this tangent bundle, then we get like we get 2, 1, 4 polynomials, and then they become the defining equations on the resolution side. And similarly, the 1, 3, and 0, 5, which were the defining equations on the deformation, show up in the bundle here. Let me just move this. All right. Okay. So, and the nodal limit is given by this linear. So basically, we write this in the determinant form and demand that the determinant vanishes. We get the nodal quintic. So I mentioned that the gauge singlets, which correspond to geometric quantities, the Kähler moduli, complex structure moduli, the bundle moduli, the sum of them remains unchanged, and we can see that it happens here. One thing to note is the counting is done in supergravity limit in leading order of alpha prime. So let me demonstrate how this moduli count works. So in our example, the total moduli is 426. On the deformation side, the Kähler modulus is 1, complex structure 101, 324 bundle, and then they sort of recombine, and that's what I'll be talking about mainly in this talk, is showing you a concrete way in sort of in tracking which modulus goes where. So one thing to note here, the Kähler modulus, there's an extra Kähler modulus on the resolution side. I'll talk about that as well. Now this matching of the moduli, they simplify, particularly the bundle moduli simplify. If you remember, I said the bundle splits into a spectator piece and the ideal sheaf piece, and the curve supporting the ideal sheaf basically has these branes which sort of recombine at the nodal limit, and it suffices to just look at the brane moduli instead of the full bundle moduli when doing even like dimension matchings or tracking the whole sort of degrees of freedom. Now, in our example, the count looks like that, where now the bundle moduli is 38 on the deformation, 52 on the resolution, and then they match, as we can see. But the whole goal is to go beyond this, just matching. One observation we do from our example is the brane is given by 2 1/4s on the deformation side, and it's given by 1, 3, and 0, 5 on the resolution side. So at least the degree level, these seem pretty sort of these seem to hint at the usual bundle manifold exchange. So if we just look at the degrees of defining polynomials on deformation resolution sides for the manifold and the brane, we see that we have a 1, 4 here, 1, 4 there, and a 1, 3 here, 0, 5 here, 1, 3 here, 0, 5 there. So this hints at like the usual exchange, but I will show that that's not quite right, and we have to be more careful with how the polynomials or like the degrees of freedom which are 0 in those polynomial classes, how they track. So let's outline the strategy. So you want to understand field mapping of this possible duality. The problem with directly approaching it from for the EFT point of view is that the Kähler potential, for example, is unknown. So we'll take the geometric route. Rough idea is all these complex structure bundle and brane and the scalar complex structure brane moduli, they mix. For example, 86 out of 101 on the deformation end up being remaining complex structure on the resolution. 14 of the complex structure become brane. One complex structure on the deformation becomes this extra Kähler modulus on the resolution. So I'll show how this happens concretely. So idea is to exchange. I mean, one simple idea could be to, as I said, right, exchange roles of polynomials as hinted by GLSM, target space duality. The problem with that is it's not the quite the right way of doing it, and I'll demonstrate. But our strategy essentially will be to go to the nodal point because the geometries become the same in the nodal limit, and then we will track exact degrees of freedom or terms in the equivalence classes of the moduli, and track where they go as we go on the other side. And that's what I'm referring to as physical degrees of freedom. Because, for example, if there's a term there in the equivalence class of that modulus, then that is zero in it. So that leads to unphysical change. So we'll spot terms which are not there and see where they end up. So before that, let me demonstrate what happens if we just do the usual exchange. So for example, there is this 1,4 polynomial on the brane equation on deformation side. If we change it by an arbitrary linear times the 1,3, 1,3 being like one of the defined equations, I can choose it to be x naught, which was my 1,3 coordinate, because we have coordinate redefinition freedom. Then, since this term is in the equivalence class of this 1,4 polynomial, on the deformation side, it leads to unphysical fluctuation. However, on resolution, this kind of a term is missing on the manifold, which the two 1,4s, right, which were my manifold defining polynomials. So this kind of a term is missing. That means it's physical. So just generally exchanging their roles doesn't quite work. So what works? So what works, as I said, is we map physical degrees of freedom in each equivalence class to a physical degree of freedom. So without going into a lot of details in how we arrive at these equivalence classes, let me just display them and then describe what we're doing here. Just to start with, we see, for example, this 0,5, this degree 5 polynomial, which is defining polynomial on the manifold of the deformation side. This is a manifold degree of freedom, the complex structure degrees of freedom. We see the usual terms. This is scaling invariance. This is coordinate redefinition freedom, right? And there's similar terms in all of them, except these highlighted ones. So let's look at the brane moduli on the deformation side. We have this arbitrary linear times this P13 polynomial. So this being present in the equivalence class means a change of that sort of polynomial in these 1,4. So if I change the 1,4 by that, leads to unphysical change. However, it's missing from this 1,4, for example. So the 1,4 or 1,4 defining equations on polynomials on the resolution side, if I change them by a term like this, that leads to a physical change. So what we're going to do is we're going to track such terms. Now, to be clear, I will talk a bit more about it in the summary. But a crucial point here is one might ask, right? Why am I allowed to identify the 1,4s on resolution side with 1,4s on deformation, or similarly for other degrees? That only could be done in the nodal limit, and then I assume their form to be this linear times this 1,3 coordinate, and this quartic times the degree 1 coordinate. And this x naught, as I said, I can choose because I have coordinate freedom. Now, there's an ambiguity which we need to be aware of because the degree 5 could be decomposed into, when we divide degree 5 by polynomial long division by this degree 4, then we get some linear quotient and this remainder piece. Now, if we look at how the polynomial long division works, we can adjust this linear quotient and the remainder piece. So this decomposition is not unique. So there's already an ambiguity which is presented. However, I'll argue that ambiguity doesn't matter. So just to summarize, what we did here is without writing all these sort of usual scaling invariance and coordinate redefinition terms, these are the terms which we're left with, and then we see that the extra term is missing here. So which means that if we change this degree 5 by arbitrary linear times this quartic, that leads to physical change. Whereas if we change the degree 5 on the resolution side by a similar term, this L, it doesn't lead to any. So we track that this degree of freedom here goes to this degree of freedom here. So for example, these are correlated changes. I hope that's clear. So I said, that there was an extra Kähler modulus showing up on the resolution side. Just to see that and motivate how it comes about is if we scale our nodal polynomial, which could be written as this, as I said previously, by some scale alpha. And then we see that this alpha scales L and Q both. So on the resolution side, this doesn't show up as a complex structure because they scale invariance of these kind of polynomials in resolution side. However, we decompose our quintic as this nodal piece and this remainder piece. So this scale only affects this part, the nodal piece. So there's already an imbalance between, or a sort of contrast between the nodal piece and the remainder piece, and this is one extra degree of freedom, which is a complex structure degree of freedom. And the proposal is
Sunit,
that
you have
if
5 minutes. Sorry.
Thanks for the reminder. Yeah, and the proposal is if we make this very large, then we go to the nodal limit, and going to the nodal limit on resolution side means that the extra cradle modulus which is there vanishes. So we conjecture that this scale alpha, this extra complex structure, maps to the Kähler modulus on the resolution. However, we don't know the exact functional form. All we know is it's inversely proportional. Now, this is all good. We have proposed a nice modular map with an ambiguity. But how can we be sure that the two theories are dual? So we look at the perturbative superpotential, and particularly the Yukawa couplings in it, which depend on complexity and brane moduli. And they could be found by calculating this map, 3 copies of H1 going into H3, H3V. And we can utilize our modular map to find it exactly. Again, I will just display the results here. Now, if you squint your eyes and look at these two expressions of the 27 cube Yukawa couplings on deformation resolution side, you see that they're the same after we plug in our modular map, except that we have this x1 cube, which is a common factor on the resolution side. So this shows that the Yukawa couplings match. One particular interesting detail about Yukawa coupling match that it doesn't depend on this ambiguity which was there in decomposing our quintic into nodal piece and the remainder, because the nodal piece is proportional to these degree 4s, and the degree 4s are in the Yukawa equivalence classes. So they're unphysical in that way. So in conclusion, what did we do? We propose a way to go beyond just massless spectrum match and just dimensional counting to exactly tracking sort of terms in the equivalence classes, which are degrees of freedom, which give us a modular map. So we gave a strong evidence for the duality by showing that Yukawa couplings in the 4D EFT, they match. Particularly in our example, we showed that the holomorphic sector. Yukawa coupling match bypasses the ambiguity which I talked about. And then one might ask that, oh, okay, well, is this duality only valid when there is some special tuning in the bundle? And it is shown that no, it's valid everywhere in the modular space. And this essentially broadens the scope of possible duality from from just like the 0 to GLSM target space duality examples to all examples connected by conifold singularity. Very quickly, the other interesting results and some future directions. So one thing we have seen that I talked about the special tuning and having some special sort of structure for the gauge bundle. So instead of gauge bundle being defined by just kernel of F, we can sort of quotient it by some additional sort of kind of gauge symmetry. And in presence of such enhanced symmetry, we can show that the Anderson-Brody-Gray prescription for conifold transition, heterotic conifold transition, can be extended. It can also be seen that this enhanced symmetry is retained across duality, so it is not broken. And now we have a way to construct examples with this enhanced symmetry, which are not the usual standard embedding. So these E maps are general polynomials than just like the coordinates, for example. Then the biggest hurdle, which I was like avoiding all this time, is the Kähler sector. And our map is incomplete and does not give us the functional form of this extra Kähler modules which showed up on the resolution side. So one way to tackle that is through sort of these instanton contributions. There are several subtleties in that. I will just mention two here. So why are we going in that direction? One, I mean, because for example, we have strong evidence, as I showed through Yukawa coupling match, and like just the holomorphic sector matching to, I mean, the perturbative part matching to perturbative part is that uh, these effects do not mix. So perturbative goes to perturbative, non-perturbative goes to perturbative. There's strong evidence for that, at least in this case. So one way to do is look at these worldsheet instron contributions, particularly when these avoid the Beasley-Witten criteria, and have non-vanishing Pfaffian free factors. And I think Mankey also showed how to get like this extra constant upfront, which was not through string field theory computation, which were not there wasn't an easy way to do that before. The upshot is basically if we look at terms like these on both sides and match them, then we can conjecture a modular map for the extra Kähler modulus on the resolution side, and this can help us find the functional form. That is all I have for now, and I would be very interested to report further on the progress made in this direction. Thank you for your attention.
Thank you. Any questions for Sunit?
Yeah, can I ask you a question?
Go ahead.
Thanks for that talk. They're very interesting. Can you say a little bit more about this perturbative maps to perturbative and non-perturbative maps to non-perturbative? I was thinking if you have a conifold transition and the Beasley-Witten criterion does not apply to the on the resolution side, would you expect that there's a superpotential that becomes sort of an order one constant as you shrink the curve, and then it should map to something perturbative on the other side? Does Beasley-Witten always apply in this case?
No, there are cases as shown, for example, by Bertolini-Plesser, particularly where the instron modular space is non-compact. That's where the Beasley-Witten criteria does not apply.
Sorry, so actually the one, I think there's a crosstalk. The one Jacob is talking about is the ones we showed do always vanish because of Beasley-Witten. They're the non-perturbative effects that would involve the new Kähler modulus. So what you're saying is right, of course, isn't it? There's many cases where it doesn't cancel, but the ones that Jacob's worrying about always do, and that's been proven.
Mm-hmm. That's because
they vanish, yeah.
That's because there is a geometric transition, and hence the GV invariant or the number of nodes is always bigger than one. And
you could just show that if you look at the structure of the bundles that Sunit was talking about, and you plug them into the Bertolini-Plesser conditions, that they always satisfy them, so the instanton moduli space is compact, and the assumption is then that Beasley-Witten holds.
So that is then the reason why perturbative maps to perturbative and non-perturbative to non-perturbative in the sense that you...
Naively, but as Sunit said, I've still found it a surprise, but, you know.
It sounds very surprising, yeah.
Yeah. But, I mean, so far, that's just what we're seeing, so...
Yeah.
Yeah.
Cool. Thanks.
Other questions for Sunit? We still have a minute or two. I don't see any hands. If not, we can thank Sunit. At the end, if someone thinks of a question, we can come back and ask a question. Very good.